Okay, good evening everybody. I hope everyone's having a wonderful day. So before I get started, I just wanted to point out a couple of things. First, assignment 1 is out. It is due by the end of the 2nd of February. As I mentioned previously, I normally keep the assignment submission window open until the following morning, until 8:30 in the morning. So just keep in mind that even though I say the end of the 2nd, I leave it open until 8:30 that following morning. If you submit any time in that window, there's no penalty or anything. So you may use that time if you'd like. The meaning behind it is mostly because if there's ever any technical issues, or for example, keep in mind, I'm not going to look at your assignment at 3 a.m., right? Nor the TAs. So the rationale behind it is like, okay, if that time is available to you, I may as well let you have it. I think it's pretty reasonable, at least for the sake of both being an online class for accessibility purposes, but also I just want to make sure, it has a very simple rationale behind it. So, and this will be true for all the assignments, by the way. But if you go past 8:30 in the morning, ooh, that's not good. I may not consider it after that, unless you have an accommodation set up with me. The other thing is, if you haven't already, make sure you do the onboarding quiz on your courses for a course website. Keep in mind that you have to do this for each of your classes. So just keep that in mind. So anyways, I want to pick up to where, well, actually before that, are there any questions about these two? I must stress that I won't have a whole lot of time to talk about the assignments in class just because of time constraints we have. However, very happy to answer questions about these assignments before and after class, during office hours. I'm really happy to answer on these kind of things. Question, how do you mark assignments? Well, I have 2 markers. I give them a marking guideline. So I prepare them that they get access to the same solution that you're going to get. And what happens is I typically rotate the graders each time we have an assignment, and all the problems are graded on a point scale. So for example, if you look at the assignment, I allocate how many marks each problem is worth. And depending on how people respond and how correct it is, you'll receive a grade for each one of these problems with respect to that. I must stress that one thing I'll point out is that for some of the assignments, there will be bonus marks. These are their locality is strictly to the assignment itself. So for example, there's 2 bonus marks for one extra problem involving big O notation at the end. If you do get this completed and it's correct, you may get 2 marks. But I must stress that the assignment is out of 20 marks. So if you get more than 20 marks, you will get 20 marks. It's just sort of a cap on how much it's worth. It's not a currency you can use. Why? Because I'm only assessing you on certain things for each assignment. So it's not supposed to be a currency you can reuse for something else. It's just an exercise so you can try it out if you like. But yeah, hopefully that helps answer that. Like I mentioned, when the assignments are graded, you'll have 2 weeks to bug the TAs. The TAs will tell you who they were and so if you need to reach out to them about grading issues, you can contact them. And if there's any issues beyond that, I'm happy to look at those things. But you have to go to the TA that graded your assignment first. But yeah, no. Lovely, lovely. So, anyways, that being said, why don't we get to where we want to talk about things here today? Because I have plenty I want to chat with you about today. So last day, I ended off talking about complexity. Now remember, complexity is about the resources that our algorithm needs. So very often we want to study complexity based on the needs that we need to solve a problem. So for example, if I want to compare 2 algorithms, I would like to know the resources necessary to compute with that given algorithm for a given problem, right? See, it's pretty natural. Furthermore, another neat fact about this is that once you have several algorithms for a given problem, you can always look at your problem to ask, okay, what's the most efficient way to solve this problem? That's another question you can address from a complexity standpoint. The resources needed for our algorithm to solve the problem. So you might ask, okay, so how do we measure this complexity thing? Like, how do we do that? So a standard way of doing this is that if we want to measure the complexity of an algorithm, for example, with respect to time, that's usually the number of operations or how long it takes for the algorithm to compute, or the space. So this is how, for example, how much memory your algorithm will require. We derive this as what we call a complexity or growth function. So you might ask, okay, so how do we do that? So I got to first describe what a complexity function is to you. If you've seen functions before, it's essentially the same thing. It's just that it's restricted to a very specific scope for things that make sense when we're computing on a computer. So if I give you a complexity function, if I call the function f, so that's its name, the parameter for this function is the size of the input. So remember we talked about input size. That's what the input is for this complexity function. So if you're wondering why do we care about input size? It's the input for this complexity function. So we measure the size of the input with respect to how long it takes or how much memory it takes. So oftentimes when we write down one of these complexity functions, often as an abbreviation, we'll write the name of the function with its input, just to make it clear for the reader. However, for those that are astute about how people write mathematical functions, you might look at this and say, Dan, that's a little confusing if you actually think about it. Because you remember a function. Remember a function, like imagine, you can think of a function just like a machine. And say the function's called f, for example. And I imagine I'm giving as input n. It does something in here, and then it produces output. What do people call the output of a function I call f with input n? Can somebody tell me? Yes, it's f of n. Very good, very good. So do you see how my abbreviation, technically speaking, is an abuse of notation? It's a very common abuse of notation, but I just feel like I need to acknowledge that it is an abuse of notation. It's just that I want to use this as a shorthand to say it's a function f where the parameter or input to it is the size of the input. Is that clear, everybody? So this isn't like the output of the function. This is just what I'm calling the function. So when I read that, I would just say it's the function f. But I'll implicitly assume that I'm giving you what the input looks like. Yeah. Yes, exactly. So when I talk about this is going to be what we're going to use to measure the complexity. So what you might ask is, okay, so what does this function look like? So what we're going to assume in this course is this is just a function, just like what you know from the dreaded M word, the mayonnaise. The input, I'm going to always assume is going to be, at least in this course, for most circumstances we're going to run into, I'm going to assume it's what we call a positive integer. So often I'll write this as a blackboard Z, which means the set of integers, with this plus meaning positive. So this n here is always going to be a positive integer. Now, if you don't know what a positive integer is, that's just simply the set of numbers that start at 1. 1, 2, 3, 4, 5, 6, and so on. That's what the set of positive integers is. In contrast, the set of integers itself, that's just simply 0, 1, 2, all the way up, and also the negative integers. So what it does is it takes a positive integer, and then as output, it produces what we call a non-negative real number. Now, you might know what a real number is. These are your fractional numbers, such as like a half, 0.78, and it also includes the irrational numbers, like for example, you might know pi, for example, or square root of 2. Actually, square root of 2 is a wonderful example. So that's the set of all real numbers. So these are all your real numbers. when I write this greater than or equals right beside it, that's just simply saying the numbers are 0 or above. Yes, if your definition of the natural numbers starts at 1, yes. I usually use this as opposed to the Blackboard N, because some people, depending on who you talk to, use the natural numbers starting at 0, which is kind of weird, but I just want to make sure I'm clear with everybody. But it's okay. Some people use different symbols to mean different things. That's why I have to talk to you about these things. So, anyways, all it is just a function. We're just going to use it to measure our complexity. So, for example, if I were to say, okay, well, if I have f, and I say, like f of n is n squared, that's an example of a complexity function. We're going to encounter lots and lots of different kinds of functions like this when we run into efficiency issues around our algorithms and data structures. So that's all it is. It's just a fancy name for a function that just takes it a positive integer and spits out a non-negative real number. And that non-negative real number is supposed to represent how long the algorithm takes for a given input. What's the last one? This right here? This is just a period here. So this is just a function, I'm just giving you an example of a complexity function. So for example, this quadratic right here is an example of a complexity function. But yeah, it's f of n is equal to n squared. So don't worry, I will show you. So remember, the whole idea is I want to measure the complexity, the resources required for our algorithms. So the way we're going to facilitate this is using these complexity functions. So we have to derive one of these functions. So we got to formulate it. So you might ask, Dan, how do we do this? We're going to need to figure out some way of analyzing the instances of the problem with respect to our algorithm and how the algorithm behaves. Why do we have to do this? Is because, for example, suppose I give you a whole collection of instances, all arrays, for example, all of equal length. Say, for example, they're all like length 5. You'd agree with me probably that there's certain sorting algorithms that even if I give you an array of length 5, they're all going to maybe have some somewhat different behavior. If I were to ask, like, okay, so how long does the algorithm take? Even if the array is of length 5, I can give you one instance of an array of length 5, and it may take a little longer than another one. So I need to have some way of pinning down the instances that cause the algorithm to have certain behavior. Why? Because it makes it easier for us to formulate this complexity function. And why would we like to do this is because very often we're interested in certain scenarios for our algorithms. For example, one that we're going to focus on a lot in this course is how long it takes for the algorithm to terminate in the worst case. This is what we call worst case analysis, for example. This is of interest for us because we would like to know how long the algorithm takes to finish as the longest possible scenario. So you're going to find that we're going to identify these by using different kinds of analyses. So is that clear? Just to give you an idea. So we're going to pick up some kind of analysis so we could study our algorithm. And then what we do is we derive one of these complexity functions based on how the algorithm behaves. And then what we're going to do is we're going to see today is we're going to count up operations that the algorithm does in that situation. And that's how we get one of these functions. Yes, so what I'm saying here is that the non-negative real numbers, this is including 0 here. But I must stress that you might ask, Dan, why is it non-negative here? Now, keep in mind, I could have defined this as a function where the output is always going to be a positive real number. Now, you might ask, Dan, why? Sometimes we're going to run into functions where the output is going to be 0. However, in real life situations, when you actually write up a computer program, the number of operations they're always going to do is typically 1 operation or more. If you had an algorithm that did 0 operations, it would literally be an empty program that had no instructions in it. But that's very strange to run into, at least in most settings. But I just feel like it makes it easier for us to work with a function that allows it to be 0 as well. But in most settings, you don't need that. Usually you will just have it where there's at least 1 operation that has to always happen. And that's typical in computer programming, right? Usually you have something that causes the function or a program to terminate, right? It's kind of weird to think about a program that doesn't have any instructions to it at all. Like, I mean, literally none. But it's just more of a helpful thing for us. Okay, so I want to talk about these analyses now. So I'm going to give you another piece of this puzzle. So we've got to talk about these different kinds of analyses that we can use. So these are 3 very common kinds of analyses you're going to run into if you ever want to study or look into different kinds of data structures and algorithms. Some of these are going to be things that we're going to focus a lot on. Some are maybe not so much in this course, but I want to make sure you're aware of them and understand at least the idea behind it. So there are 3 main kinds of analyses that you'll run into very often when we study data structures and algorithms. The first one I'm going to talk about is best case analysis. It's quite simple, and you might ask, okay, why do we need different cases to look at? Like I said, I can give you several different kinds of instances. Like, for example, if you look at the sorting problem, I can give you several different instances, all with the same input size, that all, in fact, have different behavior. And that makes it very difficult for me to formulate how much resources my algorithm is going to need. So we identify an optimistic scenario, one that maybe is based on, say, a uniform distribution or a situation where probabilities for equal likeliness are going to happen, or our most pessimistic scenario, so that we can see what happens and how long, for example, our algorithm takes. So in this scenario, we have the best case scenario. So I thought we would use the example of linear search, because we've been talking about linear search quite a few times in this class so far. I have a question for you. So you may have seen maybe some of these ideas before when you were talking about some basic problems. Does anybody have any ideas of what would be the best, like what would cause the least number of operations to happen if I give you an array and a key, and I want to find, say, that key in the array? What would be a situation that causes the least number of operations to happen? So what would it look like? What would need to happen in our, like what would the input look like? It's in the first spot, exactly. It's in that first spot in the array. Very good. So what I would do is I would just say, hey, look. So I could say in linear search, best case instances are those where key X is in the first position. Because remember, linear search will sweep from the left to the right, so if it's in the leftmost spot, it's going to be sitting right there. So if you ask how many comparisons are needed to figure out where it is, in this case, you just need one comparison to make this work. And indeed, in the chat, it was pointed out that this will take what we call constant time, what we'll call big O of 1. This will be what happens in this situation in the best case. So the whole idea behind this is that I want to identify a scenario for which all of the instances in that scenario cause the least number of operations to happen. So always think of it in the most optimistic way possible. Now, does anybody have any ideas why maybe this a type of analysis may not be the most insightful for us if we really care about how much time we need for the algorithm to terminate? Any ideas? Yeah, sometimes it can be very optimistic. In fact, it may be completely inaccurate. So for example, if I were studying this, for example, in this situation, notice that this doesn't really count for cases where where the key is, say, in the middle, or say even like not that far from the beginning. It might be not quite accurate if I really want to know and tell you, hey, look, this is what the algorithm requires to compute. So this is insightful and helpful information, but it doesn't really address the question of how long is the algorithm going to take in like the worst possible scenario, which this doesn't do that. It gives us it is optimistic. So this sometimes is very helpful for us if we know there's a lot of scenarios where it happens to be the best case one. But it's a very helpful piece of information, but it's most certainly not the ultimate one. Now, another case of analysis is so-called average case. The easy way I could put it to you is on average. So you might ask, Dan, what does that mean? So this type of analysis requires a bit of statistics. So just to be clear, we're not going to focus as much about the specific case. However, sometimes I will want you to be aware of certain scenarios where this average case holds. So sometimes I'll tell you, okay, well, even though we say that it runs, say, this time, on average, it actually does this. So for the purposes of just making sure that everybody could talk about the result, it's not so much about, I don't want to make sure that this becomes an axe to grind for some students, because I don't necessarily know the statistics background of all the class. But I did include an example in our case for linear search in the notes if you're curious about it. The only thing I'll really want you to be aware of for linear search is that the average case is still big O of n for linear search. Why? And it's actually quite intuitive, but let me just kind of back up 1 second just to illustrate the idea here. So you know how when we analyze the running times of our algorithms, we look at all the problem instances, right? And the idea is that each one of them has a size. And I want to measure what the complexity is over all of my problem instances. So you might say, okay, now what does this mean then? So imagine you were able to take all of the problem instances for the given problem, and you could assign a probability for it to happen. So for example, and for a linear search, you may consider the case where the key X is equally likely to happen anywhere in the array. So for example, in this case, if you think back to your thinking about probabilities, if there's n positions in the array, and I assume that X is indeed in the array, the probability for it occurring in some spot is 1 over n, right? So if I wanted to carry out that analysis, all I would do is calculate the overall average, or what we call the expected value. So in this case, and actually it was pointed out in the chat, like, why is it not n over 2? Actually, believe it or not, actually it's quite close to that. I believe it's n minus 1 over 2 for the number of comparisons. Actually, let me just, sorry, not n minus 1, it's n plus 1. It wouldn't make a whole lot of sense to be 0. So if you want to get more exact about it, you can actually calculate it out as n plus 1 over 2 comparisons. So if you're curious about that, just take a look in the notes, okay? The intuition is quite natural. If you think about it, okay, so if I tell you that it can happen anywhere equally likely, that would be what we would call a uniform distribution. So I'm saying all outcomes are equally likely. What I'm saying is, okay, well, it should be somewhere about the middle after you average out all of them, right? That's at least the intuition behind it. That's why it's actually a very good suggestion that maybe it might be n over 2. In fact, it's quite close to that. It's n plus 1 over 2. But yeah, no, so that's all I really have to say about average case analysis. So just be aware that all it is that if, say, for example, I want to study my problem and I look at my running time for my algorithm, sometimes I would like to know how it behaves over all the instances. Typically, it will be over a uniform distribution if somebody doesn't tell you anything specific. So sometimes that's rather helpful for us when we're looking at things because, say, for example, you find that the average case is actually much better than the worst case, which we're going to talk about in a moment. That means that often in practice, you're going to run into those nice cases quite often, at least on average. But it doesn't mean that these worst case scenarios don't happen or these best ones don't happen. They most certainly happen. It's just the thing is you're dealing with the land of probabilities at that stage. So it helps you give you some insight into how the performance of your algorithm might fare if you have a lot of different instances and you're dealing with a distribution of instances that are generally kind of all over the place. Not really nasty ones, not terribly like really easy ones, but somewhere about the middle. So question, why n+1/2? I'll ask you to take a look in the notes for that. I will be posting that after class. Just because I don't have the time to go into it. I would love to go into it though. But it's just, we have so many things I need to talk to you about today. Because I'm really excited about that. But yeah, no, if you're curious about that, what you do is you actually take all the instances and you label them. So some instances, it'll be in the first position where X is. The second group of instances will be where the second position is X, and third and fourth and fifth, and you calculate what we call the expected value, which will end up being a simple average in this case. That's generally how it plays out. If you take a look in the notes after class, it's in there. But yeah, no, I would love to talk about it, believe me. So that leaves me the third situation. It's the so-called worst case analysis. This is going to be the one that we're going to focus a lot on in this course. We'll spend a lot of time even deriving these results for ourselves so that we can convince ourselves that what we're saying is actually true. Because that's a very important aspect of this class. It's not just about me throwing things at you. I need to make sure, and I want to make it and assure that you will walk out of this class and be able to say, hey, look, it isn't just some random fact, it's actually something I can check for myself. And that's a really important aspect of computer science. It's not just like it exists, it's something I can check for myself too. So let's talk about this worst case analysis. So I already have alluded to this. It's that we're analyzing the worst case scenario. So instead of being the optimistic situation, we're looking at the absolute pessimistic situation. So for linear search, does anybody have any ideas of what an input would look like? I get very excited here. What would be the input, or at least what would describe a scenario that would cause linear search to take as long as possible? So I see some really good suggestions. So I could go even one further than just the last position in the array, which is another valid choice for a worst case scenario. In fact, I could go even further than that. Although technically, I will tell you, telling me that it's the last position, that's absolutely fine. That is, in fact, going to cause the most number of comparisons to happen. But here's the catch. I could even give you a simpler case. So for example, I could consider in linear search, X is not in array L. So if it isn't in the array, then you have to examine all the elements. You have to look at all of them. At least that's how linear search works. It scans from left to right and it checks to see, hey, look, is this X? No, I'll go to the next one. Is this X? Nah, I'm gonna go to the next one. Oh, this X? Okay, I better go to the next one. And it goes through all of them. Now, if you told me, yeah, no, when X is in the last position, that's perfectly fine too. Remember, if it's the last position, you have to compare it against X anyway. So either of them would be valid answers for a worst case scenario here. So how many comparisons do I need in this case? We need n of them, right? We have to go through the entire We need n comparisons here. We have to go through all of them. So the big thing I really want you to be aware of when it comes to this worst case analysis and why it's so important for us is about, okay, well, what does the algorithm require with respect to time? Well, this ultimately answers that question if you think about it, because it tells you how long the algorithm is going to need for any size n. So let me just make a note, and I'm going to make sure, and I encourage you, if you're taking notes, put a couple stars beside this. This is something that I like to ask questions about. So let me make a note about this. In fact, don't just put 1 star, put like 2 or 3 stars right beside it. Okay, let's see here. So am I sounding okay? I just want to confirm. So while I'm waiting for that, I'm going to make my note here. So I'm going to say if we have the worst case time complexity, for example, if we have the worst case time complexity of an algorithm, then we know the algorithm will never run longer, than the running time in, actually we'll say by this type of analysis. Why? Because, like I said, it's very pessimistic. Okay, good. I'm glad to hear that. So on your page, if you're taking notes, put like 3 stars beside this. This is something I like asking about. So this is why we consider worst case analysis. So anyways, I want to talk about what are we doing with all of this? So now I need to talk about kind of the part that I've sort of glossed over this entire time. How do we measure this stuff? Oh, a question about best case. So remember, best case gives us the optimistic scenario. And if I'm trying to address the ultimate question of how much time will my algorithm require to compute, regardless of what the input looks like for my problem, the goal is to see how long it can run. If the optimistic scenario might miss some instances where the algorithm might actually take longer even for that same sized input. So that's why we like to look at the worst case scenario very often. But like I said, each of these sort of has its own place. But this is why we'll find that worst case analysis is very commonly studied. In fact, it's so common that if you talk to some people about time complexity, they'll just assume you're talking about the worst case almost always, unless they quantify it for you. So if they say, oh, unless they say otherwise. In fact, you'll find me very commonly doing that in this course sometimes. So I must stress that when we talk about best case, I'm talking about best case as in a scenario. So I'm not saying it's the best analysis, I'm saying it's the best case analysis. It doesn't necessarily mean it's more accurate, it's that the scenario I've created is about measuring the operations, the number of operations that happen. So in the best case, I'm looking at the best case scenario, where it causes the least number of operations to occur. This is in contrast to worst case analysis, where I want to see those instances where it caused the most operations to happen. Because we need to do that, because otherwise we might be dealing with some instances where there's some more operations that happen, but same ones of the same size, it may happen a lot less of them when it comes to the number of operations and so on. But hopefully that helped clarify that. Wonderful. So, like I said, we need a clock for we need something to measure all of this stuff. Notice I've never talked about this up to this point. You just sort of get it, right? Now I have to address this. This is a very important aspect of this. So here's another thing I want to point out. So I'm going to say we need some clock to measure time, right? And another thing, if I have a clock, I'm going to need probably some machine to do this calculation, right? So and a machine for our analysis. So the first thing I want to talk about is more of an experimental look at this idea. And this is quite natural if you find yourself using a computer and you're like, okay, so how long does it take when I compute blank? So an experimental way of measuring this will presumably, and this is me using a fancy word, presumably, I'm pre-assuming, presumably, look at me, I'm using all these fancy words, will presumably need, so there's some things I'm going to need if I'm going to try to measure how long it takes with an actual clock on a computer, for example. I'm going to first need a computer, right? So I'm going to need a computer, right? Well, if I'm writing a program, so I have some program I want to run in time, well, I'm going to probably need an operating system that can facilitate the execution of that program. An operating system. Now, if I write this program up in a programming language, what does it mean if I want to execute it? What else do I need? A compiler, perfect. Yeah, we're going to need a compiler for our computer program. That's going to be the implementation of our algorithm. We're going to need a compiler as well. So, of course, you can do this. In fact, I think even in the labs, you might get to try to do this. So, for example, if I have these things, I can carry out a computer experiment. And what I could do is I can, now, just to make sure everybody's on the same footing here. Okay, remember, when I had my problem, yes, exactly, you're going to need a time measuring function. Now, fortunate for us in C++, we have functions that can do these things, like many programming languages will. So this would be something that you would definitely take into account when you write up your program. So you'll make sure when you run your program, you time it just before and just after. You can take the difference of the times, for example. And then you could plot these out, make yourself a really nice chart, and you can see how it behaves for your instances as they get large. So you can plot this out, make yourself a nice chart. But I want to point out one thing that's rather important about this. Remember, our problems, like the search problem, are the number of instances infinite or finite? So keep in mind that the way we talked about our search problem or the sorting problem, I never really put a cap on how big these arrays ever can be, right? There's always going to be another array that can always be a bit bigger that I can always point at. So for example, I can always look and say, hey, look, for my search problem, if I give you an array with 10 billion elements in it, I can always add 1 to the length of the array and there's another instance. So if I want to talk about the entire problem from a practical standpoint, I have to pick some sample of the instances when I do this, right? So for example, I may pick 100,000 instances and depending on what I'm looking at, for example, I might say I'm going to make them all randomly using some math package, for example. Or I might know what the worst case scenario looks like what I mentioned over here. You might make a whole bunch of instances that look just like that one. You even can generate them for your program. So you can write like a little routine that makes an array where the key is always in the last position. Or you can make a big data set and then it just runs it for each of your entries for your data. You can do things just like this. But notice that truly you're not capturing the true totality of the problem with respect to complexity, right? There's always going to be an instance you have to exclude. So that's one point I want to bring up. But I have a few others. So first, this is a wonderful and respectable thing to do when you're doing a computer experiment. You can time out how long it takes, but this requires me to look for and evaluate for instances. But what did we say about that previously when we talked about correctness? Could I write a computer program that runs in finite time, for example, for the search problem to make sure that my algorithm, for example, linear search actually is correct? The answer is unfortunately no, I can't, because there's always going to be another instance my program won't be able to check because my computer only has finite memory, right? At least that's like my tangible one over there, or the one you're watching this on. It doesn't have more memory that I can always get to make and encode those instances and run them on my computer, because they might get so big that my computer can't represent them anymore. But I want to point out that, this is, the first thing, generally when you do an experiment, can be time-consuming and expensive to do. Time-consuming and expensive. Now, you might say, Dan, that's fine. It's just time-consuming and expensive. That's how a lot of experiments are. Especially, man, if you get into some other scientific disciplines, some of those experiments can be rather expensive and require a lot of dedication to pull out. I've known people that had to, like, for their experiment, go out on Christmas Eve when nobody else is on campus to go look at something. That takes dedication to do, right? So that's one thing to keep in mind. So I would like to ideally have something that's cheaper and faster to do, if I could. And like I said, recall that we must consider all instances. An experiment must select some of them, but not all of them. So for some problems, so keep in mind the problems I'm talking about are those where the number of instances is infinite. Otherwise, I could write some master program that just literally enumerates all of them. But that's just another aside. So just keep that in mind. This is the thing I was just mentioning a moment ago. Now, this is probably the most important of these points. So here's a third one. So I'm just sort of running out of space here. This is going to be something that maybe at this stage, maybe haven't thought about before. It is something that, like when I write an experiment and use a computer to do this, ultimately, one thing we have to keep in mind is it depends on a particular implementation. And the machine. and the machine it is timed on. So it depends on a particular implementation and the machine it is timed on. So, which makes sense, right? Like if you have to take it's like, say we talked about linear search. I described linear search to you. Now, you might implement it on a particular computer in C++. Somebody else could come along and say, hey, look, I see linear search. They might implement it in Java, for example, or they might implement it in C, or they might implement it in a different language. Likewise, they may even implement it slightly different than the way you did it. For example, if you don't like my while loop approach, you could have run it a for loop, for example. But the point is that if we're interested in the algorithm itself, you have to take it on the nose and accept that we're talking about a particular implementation of the algorithm, but also the fact that it's being timed on a very specific machine. The machine for which it's being timed on, right? Now I have a question for you, talking about just general kind of ideas. Does that mean that if I do a computer experiment like this, is it machine dependent or machine independent? So does it depend on the computer that I run the experiment on, or does it not? It depends on it, right? So that's the one thing I really want to hammer in. So keep in mind, you can run it on many computers, but the point is that it ultimately ends up being about what computer you choose to run it on. So it is machine dependent. And I must stress this again. So it's machine dependent. I must stress this. This is not to knock the experimental approach. It's very important, especially in practice, to try your programs out and see how well they perform. That's definitely a very important aspect, at least from practical standpoint. Likewise, like I was mentioned in the chat, that you may have many, many other aspects to this. For example, there may be external resources or other aspects of the computers that you have to take into account when you do the experiment in the first place. For example, if you're doing an experiment where it relies on 5 different computers, well, if one of your computers has really bad RAM, for example, or it just has a really poor CPU, oh man, that could affect the experimental results. So these are things that somebody, when they set up the experiment, has to take into consideration and even design it carefully. So you might ask, Dan, what are we going to do now? Well, now I'm going to show you a way that we can make this not machine dependent, but machine independent. Because remember, at the end of the day, we're trying to study the algorithm itself, not how fast it runs on 1 computer or 5 computers or 10 computers. I would like to know how fast it is. So that's nothing, just to be very clear, that doesn't mean that it won't be fast on 1 computer or slow on another computer. Their specs can be different. But most certainly, I would like to know, if I give you 2 arbitrary algorithms for a problem, I would like some way to be able to compare them in a way that is meaningful about the entire problem itself, not just if the array is of length 10, not if its length is just the length of 5. I want to know for every problem instance, how efficient is that algorithm? So does everybody understand the scope for which I'm trying to address things? So it's a little bit of a broader question than just simply, okay, which one runs faster when the array is of length 10? Which is a practical one that most certainly you should consider. So if you're looking at smaller instances of the problem, most certainly you should check these kind of things. But we're looking at something much more broader right now. And I must stress that very often when we study a lot of these problems, remember, these instances can be very big. Very, very big. So big that you couldn't even imagine them. So how are we going to do this? Well, believe it or not, and this is going to sound at first like I'm doing some weird black magic over here. As believe it or not, we do not determine the actual CPU cycles or the actual amount of memory an algorithm uses. Why? Because that's machine dependent. These are machine dependent. So remember, I want to characterize the complexity of the algorithm over all inputs and all possible implementations of the algorithm. So why not use the same machine for both algorithms? See, now this is going to be the cool part. Is actually, believe it or not, that's a wonderful idea. In fact, when you do an actual computer experiment, that is actually what you would likely like to do, right? So you might ask, okay, Dan, what do we do if I can't use any one computer and be like, okay, so it's for that specific computer. So this isn't the same spirit as abstraction. The idea that we see near the beginning of the course. So instead of it being where I look at one computer and I say, okay, that has certain CPU cycles that happen, it takes this long, this many seconds. Instead, imagine I take the idea of a computer and I abstract it away from any one specification of a computer. Instead, I think of a computer that is an abstract model of computation. So a model that's going to represent our computer. And this is something computer scientists like to do all the time. So just to make sure I'm clear what I'm meaning here, just to finish my one last thought before we proceed. So we want the time complexity. The time complexity over all inputs and all implementations. All inputs and all implementations. You could feel the fervor when I'm tapping the board when I write that. That sounds quite deep, right? It's not just one computer program anymore. Now it's like, okay, so here's the algorithm. Here's all possible ways you could write that algorithm out, at least if you're following the same set of rules. And I would like to know which one's more efficient. So it sounds quite daunting of a thing, but believe it or not, it's actually very, you'd think it's going to be something really, really complicated. But I assure you, you'll be a pro at doing this by the end of this class. So, yes. So what we're going to be doing is we need to count the operations that are going to happen. But I need some way of doing this, so that's why we're going to be talking about, is that now I must stress, that we will be counting operations, but we don't even, believe it or not, we don't necessarily have to be very careful about how we do it, as long as we do it correctly, which is going to sound a little bit weird at first. But in analysis, we assume a particular, that says particular, it sort of melted, the R sort of melted there. And that looks like a V. It's an R. It melted in the microwave, everybody. We assume a particular model of computation. So I got to tell you what a model of computation is. Because this is one of those ideas that at first you're like, okay, so why do we need that? Like, we actually have like a computer over there. Like, can't you just run it over there? Yeah, you could. You could, but I would like to know about the algorithm itself, right? It's not tethered to any one computer. In fact, I could, for example, take like a group of 5 people, take a piece of paper out and give them some pencils, and I could ask them to run the algorithm. So, in fact, it's a historical context. There was a point where if you asked somebody like, hey, look, I need a computer, they might actually point to a person to calculate out something for you. So it's not even that, it sounds kind of funny right now, but that was most certainly something that used to happen. So let me talk about a model of computation. So we need some way to talk about this. So we're going to have a model for a computer. And then what we're going to do is we're going to use and try to count operations based on the rules of that model. And this model is going to be much simpler than working with just any old computer. In fact, they will actually have very natural parallels to actual computers that you're familiar with and work with all the time. So a model of computation is a formal model that describes computation as a hypothetical computational machine. That says computational over here. Computational machine that has a set of rules for how the model computes instructions when executing the algorithm. So this model is going to be, so what's going to happen is I'm going to give you the rules for analyzing an algorithm over a model. This model that I'm going to present to you is a fairly standard one that people, if you talk to somebody that's talking about algorithms, this is a very common model they will use. So I'm showing you a model that if you were to pick up, say, one day in the future, some random paper on algorithms, and they talk about like how big of a thing, most likely they're going to be talking about the same model I'm talking to you about, which that should be a hallmark of how robust of a model it is. So this is supposed to be a model that's going to represent our typical or sequential computer. So like I said, it sounds really surreal at first, but believe it or not, it's surprisingly simple. So I want to give you some examples just to illustrate the idea. So I must stress that there's many different kinds of models of computation. And why? Because there's different kinds of phenomena where different computations can happen. So often we would like to have a model that describes the kind of computations that can occur. So I want to give you some names of some models, for example. So for example, there's some are called counter machines. There's something called a pointer machine. You might ask, Dan, what are all of these things? Do I need to know about them? The answer is no. I just want to bring them to your attention. So if you ever find yourself curious, you're welcome to look into these. Pointer machines. I might also have heard of a Turing machine, for example. That's another model of computation. If you take, for example, a course such as CS411, you'll learn all about Turing machines. They're one of the kind of the standard models of computation or universal computation. So kind of what we describe as a computer. But it's not really like our computer. Our model is going to be much more like that, but it technically does and functions with the same level of computational universality. That sounds like a lot of stuff to jump on one. So let's talk a little bit about this. So I'm going to talk about the model that we're going to use in this course. We're going to use what is called the random access machine model. It's abbreviated as the RAM model. So I'm going to give you the rules for which we're going to analyze our algorithms. And it's going to feel like, man, this is going to feel very simple. And at first, it'll even feel like I'm misleading you. But believe it or not, this model's rather good at what it does, especially if we're interested in sequential computing. So another example, in this course, we will use the random access machine which is abbreviated as RAM. It's not the same thing as the RAM on your computer, just to be clear, but it is based on the same principle. So the random access machine model. So this is our model of computation. Now, here's the cool part about this. I don't actually have to explain a whole lot about the model itself. Now, given that this is a second-year class, you may or may not have taken a systems course at this stage. Now, you may learn that there's further levels down of abstraction on your computer, down to what we would call machine code, for example. And just above that, for example, you may run into so-called assembly. Now, the RAM model, believe it or not, if you were to ever go look into this and see what it actually is described like, it's very similar to assembly. So in fact, it should eerily stark for somebody. If somebody's like sitting here and like, Dan, I'm not going to really be catching on to this weird thing you're talking to me about. There's a natural parallel between the RAM model and what you might think of as assembly, the way at least it's formally defined. We don't need to go that deep because most of our programs operate by the same rules. That's actually one facet, at least about the RAM model, that makes it rather effective for describing the running times of algorithms. So all I'm going to talk to you about is the rules for which we're going to make about assumptions for analyzing our algorithms. Here are some assumptions we can make under this model. Because remember, our goal is going to be the count operations. So I'm going to give you some rules that we can use. And the reasoning behind a lot of these rules depend a lot on this model. So I'm not going to be able to go into a lot of the details about it, but I hope that a lot of the rules will seem very natural for you. At least if you think about it. But keep in mind, if you don't like this model, if you find yourself saying, Dan, why are you making this assumption? Here's the beautiful part. You can always make or specify the model even further. So for example, if you don't like that I made an assumption that this takes a certain amount of time, then there actually do exist other forms of this RAM model that may make that assumption. For example, you're going to see in a moment that I make the assumption that multiplication and addition both take some constant number of operations. And now you might say, Dan, well, multiplication is a much more complicated operation than just addition. It's actually, you could always think of it like repeated additions. So you might say, Dan, maybe multiplication is actually a much tougher operation than just addition. Now in practice, that doesn't really, sometimes you'll find that it really doesn't make much of a difference, but sometimes it does. So one thing I want to point out is that some people might pick up this model and say to you, hey, look, what happens if I assume multiplication isn't what I'm going to refer to as a simple operation? And that happens. It's very real. So don't look at this like the end-all be-all. There's many models of computation, there's a whole family of these RAM models. This is just what I would call the more general and easier one for us to use. So if you were to say, oh, I use the RAM model, they're referring to usually what I'm going to tell you here. But there's some more specific versions, so just be wary of that. So I'm going to say each simple or primitive operation takes a constant amount of time or operations. You'll find that we're actually going to be measuring operations. So one thing I do want to point out, I will justify this at some stage while we're doing this, is that we will treat these as one step. So you'll find that I'll count up some constant number of operations, but at the end of the day, when we actually calculate what we get to with the big O notation at the end of the day, it'll be no different than if I counted it as a single step. So question, these are mostly, used to calculate the runtime. Yeah, very often you'll find that when people pick up this RAM model, it's often used in the context of complexity. At least the RAM model is. But people do study these models just for the sake of the model itself even. Sometimes people actually study specifically models of computation like these, and they ask questions about them. For example, are there certain limitations to certain models of computation over other ones? But that's like way beyond this course. We're just trying to get through the fundamentals. But yeah, the RAM model is very commonly used by algorithm researchers even for measuring the running times of algorithms. But there's different models you can use, and there's often connections between them. But like I said, I'm not going to talk about those here because that requires me to go theoretically much more deeper than where we're at. Hopefully that's understandable. So we'll treat these as one step very often. Just to be clear, when I say constant, I want to say, so we state constant as meaning independent from the input size. So that's what constant means, is that it's independent of the input size. So I'm going to tell you some operations that will fall into these simple or primitive operations. So such operations assumed are comparisons. So if you compare, for example, two objects, a return. So if you return a value, I'll assume it takes constant time to do that. Any Boolean, so logical operators, like and, or, not, these are all going to fall underneath this. And I'm going to assume these other operations. Sorry, I'm getting very excited about this. Assignment, addition, subtraction, multiplication, division, less than, greater than, equals, less than or equals, greater than or equals, and not equals. I'm going to assume all of these are primitive or simple operations. So for example, assigning a value to a variable, that takes constant number of operations. That would be an example of a simple operation. And you'll find very often the kinds of things we write in our algorithms tend to be comprised of simple operations. So first, does everybody understand the idea of a simple or primitive operation? So all of these, you could assume that they're going to take some constant time or a constant number of operations. Yeah, most of the things that we do with our arithmetic, usually that's simple. Yeah, exactly. Like I said, if you don't like, for example, I know for somebody that would be very fascinated with scientific computing, some people get very nitpicky about these two. But I'm not going to go into those details here. So, how about subroutines? So let's talk about subroutines. So I'm talking about, for example, when you have a function that calls another function, or another algorithm, and you call another algorithm within your algorithm. Subroutines and loops are not simple. They are composed of many simple operations. And the last thing, remember I told you that one issue with our computer was that we could run out of memory? Well, with the RAM model, you never run out of memory. So that's the other thing I'm going to tell you. Other than the fact that each memory access takes a constant number of steps. We have as much memory We have as much memory as we like. As we like. Sorry, my writing is just really funky in this corner. Let me reiterate this. Each memory access takes a constant number of steps. We have as much memory as we like. That's what it says here. That's like. My apologies. But yeah, no. So these are going to, believe it or not, these are all the rules. That's it. So you might ask, okay, so how do we use these? So I'm going to spend the last bit of time we have for our class today to show you an example of how I can count the operations using an algorithm we've talked about. We could use linear search. So I'm going to first show you a way that we could count all of them using these rules. And then I'm going to show you, probably next class, because we're running out of time here. Next class, I'll show you how I'll very often count the operations, but I'll also will give those notes to you in advance so you can take a look at it. Say, for example, if you're working on your assignment. In addition, next time we'll also go through another example of doing this. We'll actually pick up an algorithm such as insertion sort and try to use these rules with insertion sort. So let's do another example. Let's do let's pick up linear search. So let me just bring us on over this way. So let's talk about linear search again. So we have the inputs, we have outputs, just like we had the other day. I'm just going to write out the pseudocode that we had. So we have our while loop. And then I say, okay, I is assigned I plus 1. And then I have my if statement. I check if I is equal to n. Then I return -1. Otherwise, I'm going to return I. So what I'm going to do is I'm going to number all the lines for us, just to make this easier for us to see. So I'm going to call the assignment there line 1. The while loop part here, I'm going to call that line 2. The line inside or nested in my while loop is going to be line 3. Then I'm going to have line 4 being this if statement and line 5 being my else statement. So here's what I'm going to do is let's count the total number of operations. Let's count the total number of operations. Now I have a quick question. Is it okay if I take 2 more minutes just to draw out this table for you and get to ultimately what I want to show you? Because I'm just right here. Because I want to make sure you see this. So if you want to start thinking about this for the first assignment, I want to make sure you see this so you can think about it. I will also give you some examples in the notes for how to do it in a way that's a little bit faster than this. So I'm going to make a table. Yeah, thank you, everybody. I really appreciate it. I hate asking for these things, but let me just quickly. So the first column is going to be line. The second column is going to be number of times executed. And the third column is going to be the total time. But I just want to make sure I get through this because I want to make sure I show you this right. So anyways, I have 5 lines, so I'm going to add. Oh man, I'm going to need to make another row. I thought I had it. So I have line 1, line 2, line 3, line 4, and line 5. So what we're going to do is we're going to look at how many times each line occurs. So for example, can somebody tell me how many times does line 1 happen? It happens once, right? Exactly. Now, this is where things get a little bit interesting because if you think about a while loop, so line 2, notice that the while loop keeps iterating every time it checks this condition, whether it be true or false. So if it becomes false, it has to check this condition before it exits the while loop, right? So if we're doing worst case analysis, so keep in mind, we're right now doing worst case analysis. I'm just going to make sure I mention that. So remember, we're doing this in the worst case. So that being said, how many times does line 2 execute? So very close, very close. Now keep in mind, and I must stress that you don't actually have to be very finicky or particular about this, but I'm just going to try to do this just to illustrate a point. So remember, when this while loop occurs, it checks the condition. If it's true, it'll execute line 3. Then it comes back up here. It checks line 2 again and sees if the condition's satisfied. If it's satisfied, it runs line 3. Then it comes back up here. But how many times does this actually happen then? So this happens one extra time. That's when one of these two conditions fails. In fact, if x isn't in the array, it's going to be this condition that's going to fail. So it's actually going to be not just n, it's going to be n plus 1, which at first it sounds kind of strange, but believe it or not, you don't actually have to be that picky about it. You could have, if you wrote n here, you get the exact same result that you're going to get at the end of this. But I'm just being very careful here. So line 3, we know this is going to happen n times, right? In the worst case, because I have to go through all the elements in the array. So happens n times. Line 4 happens once. Line 5 happens once. And now I want to ask, like, okay, so what's the total time? Well, I told you that assignments take constant time, right? That while loop's conditions all are comprised of simple operations, but it's a whole collection of them. I'm going to give that a name. I'll call it C2. But remember, it doesn't just happen C2 times. It happens C2 times n plus 1. That would be the total time. It's some collection of constant number of operations. See, we have this, and the AND operation. So how many times does that happen? N plus 1 times. So here in line 3, we have C3. Remember, this is just some constant number of operations. These are names I'm just giving them. So I have C3 times n. And then the last two, I just have some constant number of operations happen in all of these cases. So now all I have to do is add these up. So let me just kind of write the final result we got over here. And then we're going to wrap things up here. So counting all the operations, we end up with, if I go through all of these, I get C1 plus C2 times n plus 1 plus C3 times n plus C4 plus C5. And now if you look at this carefully, you can rearrange this in a way that looks a little bit more familiar for everybody. So you end up with C2 plus C3 times n plus all the constants where I rip out one extra C2 out of here. So I have C1 plus C2 plus C4 plus C5. Now look at this. What kind of function is that? What kind of function is this? It starts with an L. It's linear, exactly. This is a linear function. So we would say that the running time of this algorithm is linear in the input size. And this is where your big O of n comes from for linear search. Why? Because we'll see this actually next time where exactly all these constants go. But one thing I want to point out to you is you ask, where are all of those CPU cycles? These constants could represent the CPU cycles for some computer. Remember, it's just some constant number of operations. I don't know what they are, but they're just some constant number of operations. So anyways, that being said, I apologize for going a bit longer here. I'll make up for it next time, okay, everybody? So that being said, when we come back, we'll talk more about this. I'm going to give you a little bit of an advance on some of the notes if you want to work a little ahead if you'd like. especially for the assignment. And I'm hoping that when we get back here, we'll do one more example of doing this, and we'll see big O notation. Okay, everybody? One thing just one quick thing I want to point out. This calculation I did with this table, notice I counted the lines. I'm going to include in the notes, if you group them by these simple operations, like what the assignments are, what these logical operations are, the not equals versus equals, and you counted up them that way instead of the lines, you end up with actually the exact same result, a linear function. Okay? So I'll let you think about that. So I'll say thank you very much, and have yourself a beautiful evening, everybody. I'll see you later.